Good day, and you're all very welcome to this Saturday's presentation of the CNPS, 5th of July, the day after US Independence Day. So today we're very happy to have Jeff Baugher back to speak to us again. He's spoken to us a little while ago, actually, on some fairly basic mathematical analyses which may be used in physical theory, such as special relativity. He's a man after my own heart because I'm rather theoretical as well. So what Jeff is delving into a little more detail today is calculus, Euclidean and non-Euclidean geometry versus the relativity of homogeneous infinitesimals. So I think infinitesimals is something that I'll be talking about in some depth. He's talking about what he claims is the fundamental flaw in general relativity and special relativity. So it's a fairly theoretical look, but I believe it's complementary to what we have been doing very much, in previous, and a big long email discussion going on at the moment about details of experiments and interpretation of SR and so on and so forth. And I think this is a very welcome sideline to looking at the whole question of general relativity and special relativity, not looking at the theories per se, but looking at the fundamentals and seeing how they tie in or how they don't tie in with these fundamental mathematical principles. And again, the email conversation at the moment is looking at the Lorentz transforms and whether they're this or whether they're that, and arguments about that and working out synchronization of clocks and so on. I don't think Jeff will be doing that. He's starting more from the more fundamental basis of infinitesimals. Okay, so I'm not going to waste any more time on reminding you about the fundraising endeavor for the CNPS. But I'll just say, since we're in the second half of the year, I'll say that fund.naturalphilosophy.org is the site you can go into if you want to donate. We're obviously a little short of funds. The membership dues, which are very welcome, are not actually covering the total costs. There have been cost-saving measures introduced by David de Hilster in regard to, the platforms we're using, such as StreamYard today and so on. And we've exceeded the 50% target. I think something like $2,000 was the shortfall. So please go into that. It's not too late, even though it's July. We're in the second half of the year. So again, the procedure is as normal. We have people participating through Facebook and YouTube, and we also have people in the green room. So what I'll endeavor to do is, you're very welcome to post questions. I can see people are putting them in already, although some of them were just saying good morning, which is fine. And you're having discussions between yourselves. If you have any specific question for Jeff, which you don't want me to miss, because I could easily miss it, I might say they're just having a discussion about it. Just say specific question for Jeff, please. And if it's very, very urgent, Jeff would, I think, accept being interrupted. But we would try not to do that unless it's a very extreme matter of interpretation. We'll wait until Jeff is finished, and then we'll deal with the questions. And then we'll have a fuller discussion among us. We have a number of people in the green room. I'm just looking at people coming in. So now there's Jeff. Jeff, you're very, very welcome today. Thank you so much. And we've been talking over the last 20 minutes actually about your detailed visual presentations, and I think you have a little animation which you might put at the end, because we had some difficulties getting it working, but I think we got it actually to operate in the end. So so what I'll do, Jeff, is I'll give you the floor, and you might want to preface your remarks just with a short bit of introduction about yourself. Would you like me to put up the slides now so that you can go through them, or shall I wait So, for example, that's the correct thing. So it's just that if you speak about yourself, I'll leave your video up while you're doing that, just making the introduction for a minute or so. But then, as normal, when you've started to speak, I'll maximize the screen so people can see with a bit more facilities your visual presentations, which will mean your photograph will disappear, but you'll still be actually talking and available. And if you need me, just shout. I'm in the background. So
okay. Can you hear me okay now?
Yeah, I can hear you perfectly. Yeah.
Thank
If
you,
anybody can't hear Jeff or me, just let us know if you want our volume increased and so on. Okay. So I'm going to bring myself down and give you the floor entirely. So Jeff Baugher.
Hello, everybody. Good morning. My name is Jeff Baugher. My background is I have a Bachelor of Science in Electrical Engineering. I was a PhD candidate, and I happened to be working at an Air Force base in Ohio, Wright-Patterson Air Force Base, as a student, and I became pretty interested in elasticity. Had nothing to do with natural philosophy or anything, but I happened to find out, hey, elasticity is done with tensors, and so is general relativity. And that kind of got me into what does general relativity mean. And then as I went through, there were some things which really started concerning me. So I dropped out of my PhD program to work on what I'm showing you here in this presentation. So I'm still trying to get it together and everything enough to find some type of academic affiliation if I can. If not, there's some other things I want to try to do. This presentation is what I'm really talking about is general special relativity. There's some kind of fundamental flaw in it. And hopefully by the end of this, you'll have a good grasp of what I mean by that. And there's something called homogeneous infinitesimals and how they're relative to each other. And we're going to, hopefully I go in through this and it'll make a little more sense. The actual name of my research is called, as abbreviation is CIPNI, which stands for the Calculus, Philosophy, and Notation of Axiomatic Homogeneous Infinitesimals. That's a mouthful, but CIPNI kind of covers everything that I'm doing. I have another slide here, so in case I look over the side, I'm looking at some notes. Part of this presentation, I'm going to try to make it as simple as possible to give like a non-mathematical overview of my theory and stuff. And other parts are more in-depth to give like calculus researchers or historians a more in-depth understanding of CIPNI. It's not going to be rigorous on here, though. Hopefully in this, you've had at least Calculus 1 or familiar maybe with Riemann sums and that you're comfortable with geometry. This teaching method I'm doing here may leave questions with you since something's not defined as you thought it was. So hopefully it won't be too bad. Well, the outline of my research here, what I'm going to show on these slides, first we're going to talk about the current mainstream view of general relativity and what's called the paradox of the cosmological constant. And then I'm going to talk about the current mainstream mathematics, the geometric underpinnings of GR. It's kind of like the toolbox from which mathematicians work. There's all these little things that they can use and they can try to modify general relativity with it. And they have a certain toolbox. But I'm going to talk also something about, there's something called infinitesimal analysis. That got done away with. It got taken out of the toolbox, and now what they use is real analysis. So modern mathematicians don't really study infinitesimals anymore. They study real analysis or just analysis. And we'll talk about the importance of measurement theory or measures. What do we mean when we say we measure something? And then I'm going to bring in something called the axiom of NM choice, which is number and magnitude. You can think of it that way. I'm going to compare that versus the mainstream view. There's something called infinitesimals are non-Archimedean. And I'll explain what the Archimedean axiom is. And this is kind of like the smoking gun of CIPNI to say, oh, okay, mainstream mathematics says one thing, CIPNI says something else. And we'll find out why that's so important. And because of that, I'm going to give evidence that mathematicians and geometers, they haven't really understood the relativity of infinitesimals and infinity. So we're going to talk a little bit about that. And I'm going to talk about why that makes the fundamental theorem of calculus logically flawed. And so we'll give some thought experiments of what does dy over dx even mean. From that, we'll give evidence that all Euclidean, non-Euclidean geometry is based on these same flaws and it needs to be redefined. And then we'll talk a little bit about special relativity, the special relativity interpretation of the Lorentz transformation. Now, I know Hendrik Lorentz was actually an etherist and everything, so special relativity is kind of I believe the way most people in natural philosophy look at it is an interpretation of what Lorentz meant. But it's based on flaws in Leibniz's notation. So then I'll talk about resolving the cosmological constant within general relativity that it demonstrates that it's actually a logically flawed ether theory. And then we'll talk about the end about the hard part of this, of what I'm doing here, is that there's a lot of theories out there that look to supplement general relativity or modify it in some way. And what this is, where I'm saying, no, we need to restart at the very beginning and redefine what we mean by length and measurement and why all these things matter as we have built onto them. I don't even really bring up Einstein in any of this presentation, because what I'm arguing here is more against the mathematics that he was taught and not just the philosophy of what they meant. So I don't even really bring him up in the slides. You'll find out that he's not even mentioned. So this is what the mainstream description of general relativity, if you were to go to NASA, they would say at its most basic, general relativity is a way to describe gravity by attributing to it the curvature of space-time that occurs in the presence of massive bodies. Massive objects cause space-time to stretch. So we've all seen maybe kind of the trampoline analogy where you have the ball on it and it curves around and everything, and it curves space and time around it. But there's this other problem called the cosmological constant. So while one side says general relativity is great, you have another side that says, well, actually, because of this cosmological constant problem, general relativity could just be incorrect. Not sure why, but it could be incorrect. And even though general relativity was supposed to replace ether theory, many scientists now are trying to say there's some kind of maybe a dynamical fluid out in space and everything. And that is what is causing this change in the coordinate system, this expansion that we're seeing. So if you happen to go to the Dark Energy Task Force, the report of the Dark Energy Task Force, and read that, it's kind of it really lays into general relativity. So there's a lot of problems with this. I mean, general relativity only accounts for like 4% of the things that we see out there, of the energy density in the universe. So if you have a toolbox and you want to study general relativity, there's some things that you're going to have to study in this toolbox. You have to understand calculus and differential equations, real analysis, Euclidean, non-Euclidean geometry, coordinate systems, transformations, all of these things I have listed on here. Surfaces, geodesics, these kind of things. This is the toolbox that a mathematician has to be able to understand all of this. But so if you want to develop a new theory and everything, you have to use this toolbox. This is what mathematicians use. You have what you have. But if you happen to look through the history of Euclidean, non-Euclidean geometry, you're going to find something out that there's a lot of papers on something about length. One common theme in mainstream toolbox is the concept of length or measurement. Bernard Riemann, when he said that, he wrote a paper called On the Hypotheses That Lie at the Base of Geometry. And that whole paper is filled with comments about points, lengths, lines, magnitudes. But what is so important about these? And what is so important is because lengths, area, and volume stuff can change in more than one way. And it's not the way that I had been taught originally as I was coming up through my PhD studies. So it's not just lengths, though, but the same goes for area, changes in volume, etc. So this is effectively what SIPNI is all about. Examines what we mean when we say length, area, volume, and stuff, and changes in those, and what we philosophically equate those to. Time, length of time, changes in passage of time, space, length of space, changes in wavelengths, fluid density, energy density, momentum, and much, much more. So how our length, area, volume, etc. are defined is fundamentally important. But what does this have to do with ether theories? So let me ask you a question. How would you know the difference between density in a fluid surrounded by nothingness and instead having a thing of fluid and there's locally a change of density in it? How would you measure that? Let me be more specific by what I mean. Let's say that general relativity is on the left here. And what it says is that I'm going to take energy density. I'm going to model this after what's called a perfect fluid. And surrounding it is going to be a coordinate system. So this ball of energy density is modeled as a fluid. And there's a coordinate system, 3+1 dimensional coordinate system that surrounds it. And the density of this fluid changes the points in the coordinate system. So you can think of general relativity as that. Let's say the flip side of that, the other side of the coin, is imagine that you instead have an elastic medium, we'll call it a perfect fluid. and you have a wave in it. It's a change in the density of this medium. And the elements of volume around it represent density of the medium. And the change in the side of these elements represents energy density and time dilation. So it shows that time dilation is a function of this change in this energy density, of this density. How these things look like mirror images of each other. How would you know which one is right? Well, the one on the left also has got a problem in that the coordinate system seems to have some kind of fluid around it now, and it's changing the whole coordinate system evenly. So you have like these mirror images of each other. Which one of these would be a better model? The one on the left is how general relativity works. It has coordinate systems, uses what's called energy density and momentum, but uses density and pressure of a perfect fluid to model that. On the right, and it's using coordinate systems. On the right side, I'm saying, well, what if everything is just a fluid and we're just looking at changes in the fluid and it's a wave in it? How would you know the difference between these? So on the left, you have this rho vac, this density of the vacuum, which isn't understood. On the left, you can say, well, I have a rho vacuum, and energy density is just a change in the vacuum density. So the left side uses changing elements of volumes with change in a three-dimensional coordinate system. If you use time dilation as change in one-dimensional coordinate system, and a change in volume and length can offset each other. So I could have my volume change, and then I could have my other coordinate system over here change. So they can offset each other. So I could have space and time could offset each other where one changes in the other one. You can Google something called the Ricci tensor volume, and it will talk about voluminal elements as when it equates those to coordinate systems. On the right, I'd have energy density as a change in the density of the elastic medium, which is a change in these infinitesimal elements of volume. And time dilation is a function of that. So the change in length is a function of the change in volume. So that's kind of a way to think of these two mirror images of one thing. So keep going here. So basically that's what this is going to be about. And I'm going to explain to you, if there was a problem, where did this start at? Where did the mathematical notation, the flaw, come in at? I'll explain to you. Calculus originally was derived and conceptualized from infinitesimal analysis. And what that meant was you could analyze summing differences, summing and differences when lines, area, volume, etc. were divided or shrunk into infinitesimal pieces. There were things like methods of exhaustion and those types of things. And there's lots of different ways to look at calculus. This is a different way itself. So let's just say that, well, we could define dx as some kind of infinitesimal element of length, right? So delta x, we say dx, you say, okay, delta x is some length and dx is just some little infinitesimal length. I think most people kind of get that. And Euclidean, non-Euclidean geometry, but it was developed utilizing the concept of straight and curved lines. It was not developed using infinitesimals. But the problem is that infinitesimal analysis, it produces paradoxes. One of these is what's called the stair-step approximation for the Pythagorean theorem. And so you can't say that the hypotenuse of it, if you try to approximate it with a stair-step, what you'll find out is that it looks like this hypotenuse looks even the same length as a plus b on the sides. So that's not good. So because of all of these paradoxes, infinitesimal analysis fell by the wayside because you started having concept of functions, epsilon delta limits, real numbers in space. So you had this real analysis came in, and infinitesimals were purged, except for this little part called non-standard analysis. So infinitesimals are no longer considered really in higher mathematics. It's all about real analysis. There's supposed to be a video here. I'll show it at the end. It's just a video of showing you of the Pythagorean theorem. It's a triangle with a stair step on it, and how even if you get them down very small, sides would still equal a plus b, and not c squared equals a squared plus b squared. I'll show you at the end. So back in the 17th century, there were these people named Cavalieri, Torricelli, Galileo, and they were all trying to come up with calculus and understand what it meant. And it was kind of amazing that you could use these infinitesimal changes to actually measure something. But the problem is that did a line, if I have a line that's one dimension, was it made up of points or was it made up of little segments of line? Which one was the correct way to look at it? And these points didn't have any dimension, but you could have little segments of line and these infinitesimal elements and everything, but it was kind of confusing on which one it meant. But that also meant, if I wanted to sum up area, could I use little one-dimensional elements of lines, like books of a page that had no width? Could I still create area out of that? Or did I have to use these little parallelograms that are infinitesimally wide to create area? So there's this philosophical problem about what this meant. There was also what's called Torricelli's parallelogram problem. So imagine that you have this parallelogram and you divide it down the middle. As you can see, that the top triangle, the yellow and the red, is equal in area to the blue and the green on the bottom. And so is the red and the blue are equal in area, and the yellow and the green are equal area. Well, what Torricelli wondered was, like, if I took this point E all the way up to B and the green and yellow became infinitesimally thin, the problem is that they have equal magnitude of whatever you want to call it, infinitesimal area. But the problem is that they're not the same width. And this problem here was Newton pondered over it quite a bit about why this could be, that you could have these two infinitesimal slices that did not have the same width. So let me bring in something here to natural philosophy, and this is called the Archimedean axiom. And it's not that hard to understand. Imagine that I have some value of x, and I multiply it, say, 4 times. It can be bigger than some other number. It's a pretty simple kind of thing to say, is that, well, I can always multiply something by something else, and it'll be a bigger number. And this is what's called the Archimedean axiom. But forever, the infinitesimals have been considered non-Archimedean, meaning that no matter how many times I multiply a number by an infinitesimal, what they say is it'll never be greater than, or it can only be greater than or equal to 1. And why 1, I'm not exactly sure on the definition of that. But they're saying no matter how many times you multiply an infinitesimal, it'll never be greater than 1. And this is saying that infinitesimals are non-Archimedean. But I consider that kind of the smoking gun here, because it's not technically true. So instead, this is called the NM axiom of choice. And what that means is I can take what you could call a number, and I can multiply that by an infinitesimal. And you'll see it at the top there, that NADA, that's a number times an infinitesimal magnitude. And it can be greater than or equal to another number times an infinitesimal magnitude. And what it is they're relative to each other. So I would basically say one side I could call it 5, and the other side I could call it 10.832. This is what mainstream mathematics does not understand, is that you can, instead of using real numbers and everything, I can use relative numbers of infinitesimals and relative numbers of magnitude. So the top one is the NM axiom of choice, and the bottom one is what mainstream mathematics says. And I'm going to show you why that matters. Let's go back to Torricelli's parallelogram here. So it's pretty easy. I just have this point E going up. I have E to F, which is parallel, and I have E to G, which is parallel with B to C. And I bring E all the way up. If I were to take C to D down here on the bottom left, and you see the A to D, if I laid those next to each other and I went boom to boom, I went piece by piece as I bring that line over, I know that line C, I'll just call C to D as line C and A to D as line A. I know that line C is longer than line A. But if I rewrite it with using the NM axiom, the NADA is less than NCDC. The problem what I have here is that I am saying that the DA and the DC are same magnitude, but line C has more elements in it than line A does. So imagine I'm breaking, on the top left there, imagine I'm breaking this line up into little infinitesimal elements. And let's just say line C is 10, a value of 10, and line A has a value of 5. Then what I'm saying is that there are twice as many elements in C as there are in A, because all of the elements in each one of them are the same, right? So that makes sense. But what Torricelli was actually doing was when he did the lines perpendicular, he was holding the number n constant. He was holding the number of elements constant between the two lines. And that meant I have a choice here. So now A to D I can view it as having the same number of elements as line C does, but they're different magnitudes of the elements. So before, if you laid them next to each other, I could just say, well, one's longer than the other because one has more elements in it. This way I can do it and say, well, one's longer than the other because they have the same number, but the elements themselves are bigger. So this is just a comparison between the two on this simple example. You can have two lines and one is twice as long as the other, but you have a choice on whether you want to look at one of them as having twice the number of elements, but the elements are the same, and the other one has the same number of elements, but the elements themselves are double in size. So this is the axiom of NM choice. So n can be thought of as a relative cardinality, or what's called a transfinite number. It's infinite, but that infinite value can be greater than or less than or equal to another transfinite number. M can be thought of as an infinitesimal magnitude. It can be thought of as length, area, volume. So M applies to dx equals element of length, dx equals element of area, and dx equals element of volume. So if I multiply those by n, I can get a line length, I can get area, and I can get volume. And those are, if I want to know whether a line is longer or shorter than another one, it's relative to each other. So imagine, let's just take area real quick. So on the left-hand side, I have two areas, and let's just say I want to sum those areas together. And I'm using these little checker boxes as a kind of a teaching method for these elements of area. They're not, don't worry about the corners really. This hung up Descartes and everybody else. Homogeneous infinitesimals don't effectively have no shape. They can fit into anything. So don't worry so much about the corners of them. Just follow along with what I'm talking about here. So I have a choice. I can add them together, and my resulting area will have the same number of elements in it, and it will be twice as big because it has twice as many elements. Or what I could do is sum each individual element together, and I have the same number, but each element is twice as big. So the two squares on the right, they're both the same amount of area, but the problem is that they have different numbers and magnitudes of the to make up that area. But you could also look at this as a scaling problem. So imagine instead, I have this n times dx. Am I doubling the number of infinitesimals, or am I doubling the magnitude to get the double in area? So this is what I'm talking about, this choice. You have a choice when you want to say you're scaling something. Is it bigger? Is it bigger because there's more elements, or is it bigger because each of the elements are bigger? So let's just consider, I'm going to use this little plus sign on the top here. And I'm going to say, okay, the vertical bar is a dy and the horizontal bar is dx. And we saw from the last slide that my elements don't necessarily have to be the same. So in this one, I'm saying the dx and dy have the same magnitude. And I'm going to call this intrinsically flat. Now imagine I take a column of elements of area. So I have it 1 dx wide by n dy high. All right, so I have a column of elements of area. And then we'll call it a slice. You can call it a slice of area. If I took all of these columns of elements and I decided, you know what, I want to find out what my total area is, I could just sum up all of the number of elements, the n total, and that would give me my area. Or what I could do is sum my area column by column. So as I sum up one column of elements area, my area increases. Sum up another one, it increases. So I'm summing up my elements of area here, column by column by column. So if you notice, there's a very big similarity between summing them up column by column and Leibniz's notation for integration. You see the summation sign down on the red there on the right. F of x dx equals area. So you're summing up an integral of area. Well, what that would mean is that if y equals f of x, using the Sipnine notation, that means the length of, I'm actually looking at the length of a row of elements versus the length of height of elements. So I'm saying that the column height there, ny dy, is a function of the row length of nx dx, which means that I'm actually measuring the height of the column, by the number of elements in x. So the number of elements in y in the column is a function of the number of elements in x across. So that changes this. And now what we have here is that I am now saying, well, what if I want to differentiate? What does differentiation mean? What I have here is that I can take one column and I can subtract from it the next column. And what that will give me is a measure in the change of area from one column to another. So you can think of differentiation as I'm just looking at what is the change in the number of elements in each column here. So if the derivative equals 0, that means the change in the column is 0. It means that both of the columns are the same height. If it's a negative derivative, that means the number of infinitesimals are decreasing. If it's a positive derivative, that means that the number of infinitesimals is increasing. So this is how you are measuring. When you're doing calculus, you're actually measuring the number of infinitesimals, and not, we'll go into a little bit more on how it's viewed. So this is why there's a flaw in Leibniz notation. You got to be careful. Is that what Leibniz actually meant over there on the top right, dy over dx, is actually a change in the number of infinitesimals. And the size of those infinitesimals are relative to each other. So it's a quotient of the changes of n elements. Dy over dx in this context is just a quotient of the magnitudes of infinitesimal elements themselves. They aren't necessarily, the top and the bottom equations aren't necessarily the same. The top one is you're measuring changes in numbers of them, and the bottom one, you're measuring a change in the magnitudes. So if you happen to open up a book like this Elementary Calculus and Infinitesimal Approach, and you see this dy should actually be defined as the change in the number of elements from one column to another. So what about an antiderivative? So if you think about summing up using column sum of the total area, and you find a value which tells you what that change is from column to column, if you anti-differentiate, meaning that you reverse that process, it's too difficult, too many equations to show on a slide. But if I were to reverse that process, the reason that there's a constant of integration here at the bottom is because I don't know what my actual change in number was, or what the height of all the columns along the bottom were. I only know what the change of that columns were. I don't know what the total number were on the bottom. You can kind of think of it as if you were looking at the change in height of buildings, and I'm just looking at the number of floors and everything. I can go back and I can say, well, this is what my change is in floors from building to building, but I don't know what my absolute value of all my buildings' height were. So a constant of integration in this context is because I don't know the number of infinitesimals. And this is going to play into why the cosmological constant is also considered constant of integration, because it also looks at the change of something. So here's some thought experiments. Imagine velocity. You ever seen dx over dt? Well, in SIP9, using geometry, we're looking at the changes of elements as we go from column to column. Velocity is the change in the number of elements of space per element of time. So we're looking at changes in numbers. I'm looking at the change in the numbers of distance per change in element of time. So instead of it just being a change in space over a change in time, you're looking at the changes in numbers. That also applies to scalar field potentials. So if you have this partial derivatives up here, in actuality, what you're looking at is for every element of flat space. And when I say flat, that means all of my elements of space are the same distance. And I'm looking at how many elements of this field potential is changing every time I change as I move along. So I'm looking at different numbers with respect to each other. So also for force, and this is like Newtonian gravity, that's why it's considered flat space, because all of the elements of space are considered equivalent magnitude. And mainstream mathematics does not consider that infinitesimals can have their own magnitude relative to each other. So this is why the Pythagorean theorem, if I was trying to make a video of this, an animation, but the people I had with it had more questions than I could answer in the time that I needed to do this. But imagine that I have this square on A and I have C. As C pivots down, I could say that the magnitude of all these elements in C come down, they match A when it's right on top of it. But as B grows and I keep the number of elements in B constant, I'm summing up the elements of A and summing up the elements in B, and I get the same number of elements in C, and it expands. So that's one way to think of what the Pythagorean theorem means. But I could also do the same and say C itself is a combination of the number of elements and the number of elements in B. As the number of elements in B goes up, they get added to A, and that sum together is C itself. Let's take another look at Torricelli's paradox. So he was saying, well, let's just take a point E and go up to B. Another way to look at this is, imagine I have on the left, I'm going to split these apart and break these triangles up. As that E is going up, what has actually happened is I could say I'm taking a row of elements of area and I'm moving them down to the triangle on the top left. As E goes up, I'm taking another row, a column of elements of area, and I'm moving them over to the left, so that both of my triangles on the bottom are equal always, and both of my elements, both of my areas on the top and the right are also equal. If I want to, I could flip this over, and Euclidean geometry allows rotations and reflections. So let's just say I take that top triangle and I flip it over, and I now have two columns, and I can watch what happens as column to column of my elements of area move from right to left. On the bottom of this, of the triangles, where I have the blue circles over on the left-hand side, I have the same number of columns that are moving over, and even though they're the different heights, they're the same amount of infinitesimal area. Okay, so the same number of elements. So the bottom line where I'm circled and the top line where I'm circled has the same number of elements in it. But you see that the plus on the top left there, you can see that the elements in the top line are like this, same as the bottom ones on the ones, but they're laid over on their side. That's why you can change these infinitesimal elements, and you can still get a change in area as these columns go from one to the other, and still keep your area the same, even though these line lengths do not appear the same to us. The reason that they're not the same is because over on the right-hand side, if I wanted to treat these elements of area instead as being the same, then instead I have different number of elements on the bottoms here. So on the left-hand side, I have the same number of elements in each, 1 to 1 as the columns move over, and that's because my elements are inverted from each other. On the right-hand side, I could break that apart and keep the elements the exact same, but I'm now going to have to move 2 on the bottom for every one on the top to keep the area the same. So that makes sense. That's why the bottom line is twice as big on the right-hand side, is because the elements are the same size, and I need twice as many of the number. On the left-hand side, the elements are the same number. It's because one element is half the width of the ones on the bottom. So this is kind of what actually is happening in this graph on the left here, is that even though we see that delta X and everything and the delta Y is actually a change in the number of elements of Y, and delta X is we're looking at per column here. So the graph, that's the problem with the graphic on the left, is it's very misleading about what is actually occurring here. So you could think of it as Euclidean geometry is actually a constant magnitude, and we're just analyzing changes in the numbers of them. You could think of non-Euclidean geometry as an analysis of the changes in the magnitudes, but we're looking at constant numbers of them. That's simplified comparison because the NM properties exist in both Euclidean and non-Euclidean geometry. One of the big things you'll find when you're studying general relativity also is scale factors. What does scale factors mean? So a Euclidean scale factor, let's say I have a line length of 3. A scale factor of m would be 2. So m times 3 equals 6. That kind of makes sense, right? But on SIPNI, line length equals n dx times 3 equals 3. Scale factor in Euclidean geometry is I am comparing my number of elements relative to some other line. And I'm saying relative to some other line, I have twice as many. So my scale factor here equals 2, and I am doubling the number of elements. So m times n times dx equals 6. This is how you define a Euclidean scale factor. In general relativity, there's something called a metric, GUV, and it's defined using scale factors. So this G dx, dx is actually h dx times h dx. H is a scale factor for dx, but I've not found any derivation for h yet. I have found equations where it says, well, we're not really sure exactly what this means. So if somebody else can find me a derivation for the scale factor h that makes up the metric, I'd be grateful. But in the SIPNI side, the h scale factor for dx is you're measuring relative to another dx what the magnitude of h is. So if one dx I have is twice as big as the other one, then my scale factor is 2. So my line length doubles, in this case, not because the number of elements changed, doubled, but because the magnitude of the elements changed. And I still have 6. So I still have double the size. My line length is still double the size, but it's because the number of elements changed. There is something about why is there two dx's that has to do with the face of voluminal elements. I don't go to that in here and why you have dx, but that's more when we start to talk about surfaces and stuff. Let's talk about Gaussian curvature. So in Gaussian curvature here, you can think of it as a surface. These surfaces can bend a certain way. And if it's not bent, let me go over to my notes here. So if it's these are actually the well, what Gaussian curvature says is you have these let me blow it up here. On the top left of this little diagram here, where you see the green little mesh sign there with the yellow square, that is what they call an elliptic point. On the top right is hyperbolic. On the bottom left is what is called parabolic and a planar point. Hyperbolic kind of looks like a saddle shape. So what in the world does this mean? Well, in SIPNI, you can have voluminal elements, which are infinitesimal elements of volume, okay? And if we have these infinitesimal elements of volume all stacked together and I cut a layer of them, that's what I'm looking at as a surface. So what happens is, let me go back up here. So what I'm looking at here is that if I take imagine if I have a stack of rubber sheets, and I take that rubber sheets and I curve it and bend it, all right? The volume elements of volume in it have, let's just say they deformed, okay? And that gives me kind of a sphere, start of a sphere shape, and that's what we'd call elliptic. And the elements in there bend that way to create this elliptical shape. But if you take those sheets of rubber and you bend them to a saddle shape and everything, then the rubber deforms one way and up the other. This is what we should be using as an elastic model. And so to the voluminal elements. If you bend the sheets down on two sides, but level across from each other, that's parabolic, kind of like the side of a cone. And if the stacks are level, then that is planar. And I can take the magnitudes of voluminal elements and I can compare them, how the magnitudes change, and I can recreate what's called Gaussian curvature. And the reason this is important is that if you want to know why space should be modeled as an elastic material, is because you have to replace absolute geometry, which is dx's all meaning the same, with adjustable dx's, so that you can model space as an elastic material, which is not something like Hendrik Lorentz ever did. So another thing, there's just something called a Christoffel symbol. So this gets in real in depth. So what a Christoffel symbol, you can look at it, but what it basically means, it allows distances to be measured on those surfaces we've been talking about. Okay, and what I'm actually looking as I'm differentiating that metric to find out how does my distances change. Well, you can think of it that is just you're measuring how those distances change of those infinitesimals. You're measuring the magnitude change of those infinitesimals. So that's a simple way of looking at what a Christoffel symbol is actually measuring. Is it's using the metric to measure how much of a change there was across that surface. But in the ether theory, you're saying I'm measuring how much the ether has strained across what it would call a surface. It's not a gradient, because a gradient requires flat dx's for space, and we don't have flat ones here. We have adjustable ones. So a coordinate system here, this is a spherical coordinate system on the left. The value in NM magnitudes and stuff, you would have a cubic volume of elements of area, right? So on the left-hand side, general relativity confuses a three-dimensional coordinate system with elements of volume. So in the coordinate system, if it is Euclidean, what we're actually talking about are elements of volume that are all of the same size, right? So that's why coordinate systems look very, very convincing, but we should actually use an elements of volume instead of a three-dimensional for Euclidean space. And that is why the difference between non-Euclidean is whenever those elements can change magnitude. So philosophically, in general relativity and special relativity, you could say you have a length of time, but in natural philosophy applied to these infinitesimals, you would say, well, length of time is the number of elements times some dt, that's 10 seconds. A length of space is some number of elements, we could call that 10 meters. But time dilation would be the change in the actual size of the infinitesimal, is the change in the clock ticking locally. So we see how fast things vibrate and everything based on the strain is in the fluid. Length contractions, we would say, well, we're actually looking at change in wavelength based on the change in infinitesimal sizes somewhere in the fluid. So if you're out in space and everything is flat, you might locally curve everything, but you're going through a homogeneous isotropic elastic material, this wave is, and you're not in any strain. So your time doesn't change. If you're just moving at a constant velocity, if your wavelength doesn't change, it doesn't change until you get into the strain. Now, I won't get into too much depth of special relativity, because then we start talking about quantum mechanics. I don't want to include that in here. So you have this special relativity version of the Lorentz transformation. So I'll just talk a little bit about it. There's this ambiguity. When we say, remember how we talked about velocity being dx over dt? So when I look at velocity in here, are we talking about dx over dt, or are we talking about the number of elements dx over per change in dt? These are not the same things. So that's all I'll say about the Lorentz transformation, is it's trying to have its cake and eat it too by using two different versions of what dx over dt means. So let me just finish up here, get toward the end of the presentation stuff. So the big picture here, what's the big picture of all this? The big picture is that general relativity is energy density modeled after a perfect fluid, and it's surrounded by a coordinate system. Density of this perfect fluid affects spacing in the coordinate system, calls it curved. No density means all the points are equally spaced, so your coordinate system is flat. This unknown fluid, when it gets real dense and everything, it causes a change in the spacing of all the points everywhere. But the problem is, so that's the cosmological constant problem, is you have this unknown fluid, which is stretching out all of the coordinate system. But why is there a fluid outside this ball of fluid now? It wasn't supposed to be there. But that's the problem, is that now all of the volume of elements everywhere aren't just changing locally here. There's changing spacing everywhere. So they look at it as a tensor with 3 spatial coordinates and 1 of time. In SIP9, instead, we say that this change in volume of elements and time dilation is a function of the strain change in this density of the medium. So we still have elements of volume out here, but they're measuring the relative density of a fluid. And if all of them happen to be changing at the same time, that means that the ether across the whole universe seems to be changing as it's evolving. And it makes a little bit more sense. So energy density in SIP9 is a change in the density of the vacuum itself. If you want, so you can look up Ricci tensor, and you can see how that represents how volume in a curved space differs from a volume in Euclidean space, if you want to follow up on that. So this is why general relativity works at all. It treats space as a coordinate system. And this is why I say the fundamental flaw in general relativity and special relativity is that they are using coordinate systems instead of elements of length, elements of volume, elements of area. It's not a coordinate system. A coordinate system is a way to measure from point to point. But we realize that we don't measure from point to point. We're actually measuring the infinitesimals there. It's a hard concept kind of to grasp, but that is the difference between saying I'm going to treat these voluminal elements as a density of a fluid, or am I going to look at these as a coordinate system? So you have to find that boundary mentally to be able to kind of understand it. So it treats space as a coordinate system. It says if energy density is present, then the volume of those elements surround the energy density changes. And the problem is NM axiom requires some distance to be defined as the default magnitude of the infinitesimal distance the distance between points. GR generally appears to choose 1 and reduces that distance until singularities happen. So this is why you get singularities in general relativity, is because the infinitesimal becomes null. So we're looking at changes in the magnitude and stuff, and general relativity doesn't realize that. It just takes the coordinate system and says, oh, the points between my space have become 0. And that's how you get singularities in the equations. But as we now know, magnitudes of infinitesimals are only measurable relative to another infinitesimal. And this is what debunks the GR model. The cosmological constant is just evidence that any arbitrary element of volume could be the default measurement. And SIP9 states that the infinitesimals are modeled after a default density of elastic measurement. I have to choose some kind of density for my ether. And then I'm looking at changes in this density, and the strain. And that's what is measured as energy density. So if there's no strain in the density of the vacuum, there's no energy density. It requires strain, requires changes in the density of it locally. That's what you're looking at when you see a wave moving around. So however, it appears that the density in the medium of the universe is also changing through redshift. So when we said that the cosmological constant could be a constant of integration, it means it's a constant of integration because I'm measuring the changes in the magnitudes of the elements, not the numbers. Constant of integration in calculus is the value you're looking at what's the change in the numbers, but you don't know what the absolute number is. And in cosmological constant, you're looking at the change in the magnitude of the infinitesimals themselves, but you don't know what the absolute value of that is. And that's why it's called the constant of integration, because you need to define it somewhere. So we would say we need to define it as a certain density of the ether, but we don't know where to start at. At least that would be one problem. So this is toward the ending of my slides here. The problem is, of course, it's highly abstract. Another problem I have is that all new theories look to supplement or add on to existing theories, metric theories. If you've ever heard of MOND, that's modified Newtonian dynamics. They're looking to modify Newtonian dynamics, or all these metric theories are looking to kind of modify general relativity. They're not looking to entirely replace the foundation of it. The other problem is infinitesimal analysis was purged from mathematics. Real analysis is mainstream. So there's not even really a journals that really look at infinitesimal analysis, really, except for maybe non-standard analysis. And that itself has problems. Modern mathematicians, geometers are boxed into thinking in terms of numbers. So they look at set theory, real, irrational, rational integer, etc. They're looking at all these different types of numbers, and they're using these instead of infinitesimals. Whereas what I'm doing is I'm mapping real numbers onto infinitesimals. Relativity is widely viewed as undisputed in spite of growing issues with the paradoxes. Ether theories, of course, are no longer in vogue. Natural philosophy is no longer in vogue. And there's also this misunderstanding of the Archimedean axiom, and it's entrenched. So thinking in terms of infinitesimal numbers and magnitudes are going to require new thought experiments to be developed. And there's not really anybody who can peer review my papers, because the people that understood infinitesimals at the basic level, they died out a long time ago. Of course, that equates to no funding for research or experiments. But I do have a path forward. So what I'm going to try to do is I'm going to try to reach out to calculus teachers and students that are not familiar with non-Euclidean geometry, because bad habits aren't yet entrenched. I'm going to focus time on teachers and students who are willing to put in effort to understand the concept, but that might require paying them first to develop teaching aid, my animations and stuff. I'll give you an example between two professors here. I had hired to do my animations. The first one, he did that first animation I had about the stair-step analysis of the Pythagorean theorem. But the problem was once I started explaining what I wanted to do with it, he kind of balked and said he needed to know more. But he was very entrenched in real analysis. And he said that you could not use infinitesimals. They do not work. They have paradoxes. He would not read the paper in depth, but what he wrote to me is mathematics is full of weird domains, but the one that'll definitely satisfy your needs and get you where you need to go here is analysis. I know that with 100% certainty. In spite of what I showed in the papers and everything, he didn't really read it through. He was just very entrenched to focus on real analysis, which is a problem you're going to have getting into journals. Another professor I had who took more time to understand what it was I was trying to do, he said, it's a little late with me. He said, anyhow, the illustration of NM choice is not very difficult. I have brainstormed the idea. I used to teach Riemann and Riemann-Stieltjes integrals in real analysis subject. The concepts help me understand a completely different perspective. The concept of derivatives is now very clear to me, and many more concepts. And he seemed to think maybe this work is worthy of the Nobel Prize, but you can see there's a long, steep hill still ahead of us. But this is the pathway I think is forward, is through the mathematical and geometric side and not the philosophy side. I think the philosophy side of it will come in once we can bring in more mathematicians. So that is the end of my presentation here. And I will take it back to Ian or be ready to answer questions.
Well, thank you very much, Jeff. That was most stimulating. And, as I have been thinking quite strongly about this, that it's supplementary to the many other ways that we've been looking at the whole question of the theories of modern physics. And in fact, unfortunately, dare I say it, mathematics might have got a bad name among many of us, because we have been looking not too kindly on the mathematician going into an ivory tower and saying, I'm going to develop a theory of how the world works, and just from the equations, without doing any experiments, going out and saying this has to be the case. Right. Now, but what you've done is very, very important. I mean, you're looking at the fundamental aspects of mathematics, because mathematics, and we had a brief discussion about this before we started, mathematics is really a language, a tool, which ought to be more concise and more precise than ordinary everyday language. We're speaking with a degree of prolixity about aspects, and perhaps we're not defining things very, very accurately. And language can be ambiguous, but in mathematics, we try to get a more precise and concise means of expressing things. Now, just maybe one or two comments before we come on to the discussion and questions. So one thing that occurred to me is it seemed to me that you're concurring in many ways with some of the other ideas that have come out in other discussions, that the GR system is really just a coordinate system based on the concept of space-time, whereas the SIPNY, if you like, is actually, although it's very, very mathematical, it's more physical. It's concerned with properties, fluid properties,
Right.
which is more in line with really the way natural philosophy should be working, rather than working from an ivory tower equations to reality. It should be looking at not just a description of what happens. GR would say, this happens. This is like a puckered sheet of material. Don't ask why. That's what happens. But here we're back to more classical concepts as to what the properties of the fluid are. And you also talked about
that's correct.
Yeah.
So I look at it one side, you have the geometry, but then you have a physical model, and I'm saying that we're describing the universe we find ourselves in using the properties of fluid models. I mean, that's kind of a way, I believe, when they model stars around galaxies and stuff, they use hydrodynamic models. They use fluid models. I've heard people mention who model these things that they're sad about that ether theories are no longer in vogue because they use fluid models to model the rotation of galaxies. I mean, so we do use these wave equations, these fluid models and everything to describe the reality we find ourselves in, which is kind of, I think, all of the evidence starts pointing towards that we're some type of waves in a fluid. And I think that, hopefully this is what I'm looking at is like, well, if that's true, what could be wrong about the models we have now and what could be correct about them? So I believe general relativity is right to use this concept of perfect fluids, but they're using it in the wrong way. I think that they're mistaking coordinate systems for these elements of length and volume and everything. I think that's the problem, is that this coordinate system is blocking us from moving forward.
Okay, well that's it's the same thing. So, and you also talked about the lambda cosmological constant as being really just a constant of integration. So,
right. So you can think of it in ether theory. You can think of the cosmological constant as what is my default density of the ether. That is the point where we measure from these changes and stuff. So they look at general relativity looks at it not as a default distance between points, whereas we're looking at it as the default density of the ether that we're measuring changes from. So it's a kind of, you can still think of it as a constant integration, is where are we measuring from?
Okay. Just maybe one very brief thing, which is a different subject altogether. I hear you earlier on saying something about 4% of the known universe. So do you accept any form of dark matter, or do you postulate that in your system?
No, I think that dark matter is just I don't know what dark matter is. I don't have the equations and stuff, but I don't think that I don't think there actually is any dark matter. I think it's just because the equations end up being incorrect because we're using the wrong model. Because dark matter is supposed to be spread over this whole thing. I could easily imagine it is because maybe the density of the ether around around galaxies and stuff is not the same as what's out here in the empty space. The density there's a change in there, and it may just be due to the rotations. Maybe it's stretching out the ether or something. I'm just spitballing here, but I don't think it's actually a particle or anything. But there's no way to know. How would you know until you get the equations, which are more less logically flawed than what we have now?
Okay. I've been looking through some of the questions. I noted there's one or two specific questions to you. I think maybe from Michael Kelly or something, but I'll come to them in a second. Maybe if there's anything else we need to cover before we get to the more detailed discussion. Okay. Just
I'll
give me
look
a
forward to it.
second to get through these. Okay. Well, I mean, there was one question about obviously they remembered your previous discussion, your
Yes,
previous
it is.
presentation, the CNPS. But I said that this is really a follow-on, isn't it? I mean, you're
Yeah, this
going.
is so my research is advanced slowly, and so what I didn't realize, what I didn't appreciate before, I think on the one before was Torricelli's work. That this is where that when they were developing calculus, Torricelli had all these questions about why did it seem like you could use calculus with these lines and everything, and that these questions were never answered. I mean, they have never been answered by any mathematicians. You will find something that they say, well, it has something to do with cardinality and magnitude, but there's no equations that you'll find out there in any books that resolve the Torricelli's problem. So what you're seeing here is the only solution to it that I am aware of. When I showed the lines moving and the elements of area being different, that's the only solution I know of in the world is what you're seeing here. So, and when I showed how the elements of volume and stuff can change, it doesn't exist anywhere else in the world that I know of except in SIP9. So that's why I consider it so important, is that when I did with Torricelli's problem is not something that Newton was aware of. So when Newton and Leibniz and stuff developed the calculus, they weren't aware of this, and neither was Gauss, Riemann, Wallace, all of these other people that helped develop calculus, Lebesgue, everybody were not aware of this solution to Torricelli's problem. So that, to me, that's a 400-year-old problem. That tells me if they weren't aware of it when they developed Euclidean, non-Euclidean geometry, what would they have done if they had been? Would they have still said, oh, two lines are parallel because they're, well, how do you define two lines being parallel? I would define it in a flat space as saying the number of elements between them doesn't change. The columns are the same. So you could actually even define the parallel postulate using SIP9. That's what's kind of powerful about it, that people don't realize, is some of these fundamental thoughts about why are lines parallel? What does Euclid's axioms mean? You can define it through the number of elements using SIP9.
Okay, well, that's quite revolutionary then. Michael has actually asked specifically to Jeff. I'm not sure.
I see it. I brought it up. That's nice.
Did you see this? When you
Yeah.
bring up things like volume, density, you imply that what appears to be empty space is substantive. If there is a change in density, doesn't that imply an outer limit to space?
So what he's saying is there an edge to space?
Right.
So what I would scientifically say as a natural philosopher is that there's a limit to what I know. All I know is what I'm looking at is the language of infinitesimals, and I'm looking at the language of basically fluids, elastic materials. But that to me is not something I know yet. That is a modeling issue, and I don't know if there's an outer edge or not. All I know is a simple little thing. I have a toolbox full of infinitesimals that I'm using to model after this fluid models, but I'm using this to model the universe we find ourselves in. If there's actually an outer there, now it could be that maybe through this you can figure out what the energy, how much energy is in the universe and everything else, and the expansion of the universe and everything, or maybe even the contraction of the universe. And maybe you could come up with a theory based on this, showing that there's an outer limit to it. That is that's beyond my pay grade, so I don't know
right.
yet.
It's a toolbox, which certainly up to now has not pronounced one way or the other on these matters.
Right.
Okay. I think he has another question here before we get to the end.
It's like, Jeff, 3 times 4 equals 6 times 2 equals 12. Total area is the same whether you're using calculus or algebra. And I'm not saying he's wrong about that, but the problem is that when you use infinitesimals, there are 2 different ways to look at area when using infinitesimals. So if let's just say I have a line and I divide that line up into infinite many little pieces, right? If I divide that line one more time infinitely, does it change the length of the line? It doesn't. So it doesn't matter how many times, but I can divide that line double or more. But if I divide it again at infinite plus 1, that must mean that my magnitude of my infinitesimals get smaller. But it doesn't change the length of the line itself. And the same applies for area. If I divide it up into so many elements of area, if I divide it up again, the elements of area have shrunk, but my number has doubled.
Would some of these concepts be not totally unrelated to, Cantor's ideas of infinity?
Right. That's where transfinite comes from, is Cantor.
I understand,
so he had this concept of infinity could have different magnitudes and stuff. And it was Cantor's work is where it kind of dawned on me that you could have infinite values, which were different. So that is where I use the term transfinite from. Some people don't like that I use the term transfinite because it's different than what Cantor uses, but the basic concept is the same. Is that you can have infinite something, but you can have double infinite also. And it's kind of a hard concept to think of, that you can have an infinite number of infinitesimals and it equals a definite length. But those number of infinite is relative to another line. So that's the relativity of the infinitesimals.
Okay, well, that's important. Certainly for me, that the transfinite is basically similar to Cantor's ideas of infinity. I'm not sure if this one, what he's referring to exactly. I mean, your question, it's concerning false mathematical systems, which lead to false analysis, maybe in GR and things like that. But he said, which mathematical systems were based on false premises? Do you want to list them all?
No, you can't list them all. I mean, you got calculus of variations. You've got, anything with a dx in it, any type of differential geometry, all of these things I'm saying are all based on a flawed understanding of infinitesimals. So basically all of non-Euclidean Euclidean geometry are based on a flawed understanding of infinitesimals. They are true. There's a logical truth there, but to me, it's based on this number and the sizes of relative sizes of infinitesimals, that you can recreate everything that's been done since those were developed using this different method. So, I mean, there's just tons of them. Anything that basically got developed with the use of infinitesimals I think is fundamentally flawed, and which is why I think we can't make progress. Yeah, it's very extensive. Yes.
I may have asked this at your last presentation, actually, but I don't know what you think about Bishop Berkeley. Originally was very skeptical about the whole question of differentials, and he said when they were sort of finite, that was reality. But when you got from delta x to dx, you were talking about the ghosts of vanished quantities.
Yeah, departed quantities. Yeah.
And he objected to that. In fact, he at one stage he said it was the first step to atheism.
which was very much a big insult back then. Yes.
Yeah, in those days, indeed. Yes.
Yeah, and that's what I think. I think natural philosophers, especially the group, should read stuff like there's a book by Amir Alexander called Infinitesimals, I think it's a dangerous concept. So it kind of gives a history of infinitesimals, starting with Cavalieri on the Italian peninsula, and Galileo and Torricelli and stuff, understanding what these concepts were that developed into calculus, because that is essentially what we talk about when we say measurement. I think starting and looking at this whole history and everything, you can kind of see where infinitesimals were very, very active in increasing our knowledge of mathematics. But the problem is once you start using infinitesimals to say, hey, these infinitesimals are constant and everything, and this is how Newton developed what's called a fluxion, and these concepts and everything. Once you start studying the history of it and you start looking back here and says, did we make a mistake somewhere with infinitesimals? And that's what I believe we did, is that we made a mistake abandoning them for real analysis. So even though this NM, this axiom of NM relativity here, NM choice, I think through that it simplifies everything, so that when you look at the history of it, you can kind of see where we stopped making sense when we started getting to absolute space and absolute time and everything, because these did not allow for changing wavelengths and changing clock rates inside of an ether that stretches and everything. That's what's a pain in the butt about it, is that we get used to thinking in straight lines and stuff, and that a line can't stretch and a line can't compress. we don't think of it that way. We think if I'm going to take a line, I'm just going to double the length of it and everything. And this is, I think, how we think mentally. And when we do plots in 2D, that's what we do. When we draw lines on it and everything, we think, oh, well, if I take this line and stretch it out, I have the same line. I can compare it down to here. But we don't really think of it in terms of infinitesimals. So to me, that's what this axiom of minimum choice helps out, is it's a mental aid in understanding what do we mean when we say these things, when we're measuring length and time and density of volume and everything. So that might have been longer than what you're looking for.
No, okay, that's useful. Now, Corey has asked us, I don't know if this is in response to some back and to and fro discussion they're having on the email list here, but generally, he perhaps is questioning why one is talking about a perfect fluid and not a rigid solid, for example. Tension, strain, and transverse waves do not propagate through a fluid.
Right, and I do agree with him that it's bad wording. But the only reason I say perfect fluid instead of a rigid solid, because they used to think if the ether was real, it had to be as hard as a diamond to be able to transmit light waves and everything real fast. And that when I say a perfect fluid, I am not talking about a fluid that flows and stuff. I am talking more of an elastic, rigid, solid medium. So that was what my study was in monocrystalline silicon and stuff. So that's what brought up my questions and stuff. I'm not talking, when I say fluid, I don't mean a flow of a fluid that moves around. I am talking about a rigid, what we would think of as a rigid solid, and using continuum mechanics with that. I don't mean a fluid that flows. I do agree with him that there's tension, strain, and stuff like that, and transverse waves. I don't mean a fluid that, the only reason I use the term perfect fluid is because that's the term general relativity uses.
Okay. And you haven't gone into the details or speculating about what the composition of this perfect fluid might be.
No, and I don't know that I would know. I'm just saying, to me, it's more of a modeling.
That's another study, yeah.
That's another study. To me, I'm just trying to make this as easy as I can to say. So continuum mechanics doesn't look like as having particles in it, because I don't believe this fluid is made of particles or anything. I think that's a bad way to think of it. To me, it's just an isotropic. You're modeling it as a medium, but you're not really looking at the particles that are in it. You're looking at waves in the medium itself. So I think that's a mistake, is to sit there and think that it's a fluid that flows and everything.
Okay. I don't know if in some ways you may have dealt with this, because you had towards the end, and this question may have come in before the end, a proposal as to how one might promulgate these ideas. He's asking, for those of us ignorant of bad math, have you developed a training of the basic fundamentals of your theory or teaching method as of yet for homogeneous infinitesimals?
Well, that's so I've kind of changed my job now to so I have more time to work on this now that it's kind of solidified into a path. So that's what I hope to do over the next year. But it's hard because I think in my head, I'm like, oh, this graphic explains a lot here, like the stuff in my presentation here, but I need feedback to say this doesn't make any sense to me. So I am hopeful to work on that through the next year and everything, to have a beginning from 400 years ago and to have citations and stuff. At the end of this presentation, there is a link to my older paper from last year, but it does not have the NM axiom of choice in it, but it does have more detailed discussions about things like one forms, about one spheres, two spheres, stuff like that, about Gaussian curvature and stuff like that. So there is a paper at the end. It's on Vixra, of course. But I hopefully
people might have missed that. Was it a link in your presentation?
Yeah, it was a link in my presentation. I can probably post it in the.
You could post in the chat, maybe it might help people.
All right, let me see here.
If you have access to the general comments, it will go in there. If you have access only to the green room chat, well, then not everybody will see it. But I can
join the chat.
The private chat.
Okay, so we do the private chat. Oh, the private chat.
Well, then I think what I do is I'll take that and I'll put it into the other chat as well, just so everybody has it. The comments, in other words. So okay. It's posted there. Okay, Vixra, right. Well, it is now, yeah. Okay. Okay, I think we're new comments coming in, but we'll have to put an end to it because we want to get to the chat now. Right. Yeah, Michael is asking a lot of questions. Here's another one. Jeff, you may have seen that. Is the reason for the heterogeneous versus homogeneous view a consequence of being subjective viewers of the universe versus having an objective view from outside the system?
That's not a bad idea, because you think heterogeneous meant that we think of points. I think of a point here and a point here, and I'm thinking of the distance between them because I'm in it itself. I'm and you are. It's subjective because I think, well, if I'm going to go over here, I have a coordinate point to it and everything. If you were able to be outside of it and you were able to see, oh, it's actually a wave, and there is no such. The only reason you can have a point with zero dimension is in a one-dimensional line. But we don't live in a one-dimensional universe. We live in a three-directional universe. And if you were outside of it and you could see the wave actually compressing and moving, you would realize that what we thought of as a point going absolutely from there, you're actually seeing the points move around as we move, as in the wave itself, the points move. So I do think that might be a problem with our own viewpoint. I could see that. And the heterogeneous versus homogeneous is not my research. This is a concept that Galileo was and Newton and Torricelli were very concerned about, this heterogeneous versus homogeneous. And that's there's a book called 17th Century Indivisibles Revisited, and it's a very good book. It's kind of but because of certain concepts in there, but that's what the book is. There's a large part of it is about what do we mean when we say heterogeneous versus homogeneous. It explains it in there, but explains the problems with it. It doesn't give you a resolution. I'm giving a resolution. Heterogeneous means, hey, everything's made of points, and we just measure the distance between points. I'm saying, no, everything is made of elements of length, volume, area, and stuff, and that's the way to view it. And there's a difference between the two. So it explains why some mathematicians believe the heterogeneous view, whereas people like Torricelli believe the homogeneous view, except he didn't know to use, Torricelli used like lengths of line that had thickness to create area. It never occurred to him to use infinitesimal elements of area. If he had done that, I believe that we would have had a different path in mathematics.
Okay. Who was the author of that book that you referred to? Do you recall?
Let me here. I'll send you a Google link because it's got a lot of different mathematical authors in the 17th century.
Okay. That'd be useful. Thank you for that. Okay. Right.
So I'll send it in here, and then you can put it out. This is the link of the book because there's quite a few authors in it. The book is made up of.
Have you put that in the private chat?
Yeah,
you have. Yeah.
Chat.
Well, again, I'll put it in the general one as well.
Okay.
Right. That's in now. Okay. Excellent. Well. Okay. Well, here's a question from Robert K, who has asked a number of questions on previous occasions, a bit like this. Jeff, you seem to be incorrectly mixing Riemann summation theory with differential theory, ? The differentials dx, dy, or dz all define very small changes in those quantities. Why would this be wrong?
Well, you have to go back to the slide where I showed there, is that just say dy over dx. You imagine that an integral is just a summation of area, right? If you think of as a derivative as a measure of the change in that area, we're measuring the change in that area column by column. So what's wrong with dy over dx is that dx means the bottom of a column, two columns I'm comparing, and dy is the same magnitude as the dx. You're just measuring the change in the number of the dy's. That's why it's confusing, is because dx on the bottom of these columns and stuff, you're just measuring from one column to the next, and you're measuring the change in the height of it, which is the change in the number of the dy's. That's what Newton misunderstood, is that a derivative is actually a measure of the change in the area as you go column by column. So even though the notation there looks the same, the dy and the dx, they do not philosophically or geometrically mean the same thing.
See, the notation, I think I'm correct here, am I, is really not Leibnizian. The dx and dy. Newton just used like maybe a dot on top of the
Right.
With in very long differential equations with maybe time, we do that nowadays, but we use the Leibnizian.
Right, and you're right,
notation.
but see, that's the problem is that so notation gives us economy of thought. So we use notation to think of things through. But if your notation is based on a flaw in the understanding of the underlying geometry, you get a bad value out of it. And that's why you get confused. That's why you can't understand why there are singularities in the equations and stuff. These things don't make sense. But if you went back and you said, oh, we're not actually looking at a change in the slope and the tangent and everything, we're actually looking at the change in the number of these elements of area, everything starts to make a lot more sense actually to me. So that's why if he wanted to go through the paper that I linked when he asked that question, my Vixra paper, he can see why I think that there's a flaw in the notation.
Okay, and if there are any further questions after maybe studying some of the background, we can come back to those. That's quite possible. So we have a little more left than a half hour left. So and I try to bring as many people in as I can. But are there any hands, people who would like to raise their hand, so we can? Nick Percival has raised his hand, so I'm going to bring you in, Nick. So Nick, your comments or questions or. I think you're muted, Nick. You'll have to unmute yourself.
Yeah, I did. Good morning, Professor Jeff. Good to see you again.
Good morning, Nick. Good to see you too.
Just as you were going through the presentation, I had some thoughts that was about some of the recent dialogues and debates I've had within the CNPS, and just to make a very general point, I think some people in the CNPS view through the lens of mathematics, and others view it primarily through the lens of physics or physics models. Now, you do have to get both correct, and I'm not saying one is inherently, in general, superior to the other, but just pointing it out. And it would seem that you and I may be polar opposites in that. I think you look at it through the lens of math, and I tend to look at it through the lens of physics models. Now, in one of our dialogues, we had the similar dichotomy in views, but we both came to the same conclusion, namely that special relativity is wrong. But my counterpart said that was due to its violating some fundamental math law, whereas I thought it was because Einstein took Lorentz physics theory, where there was a single preferred frame, and transformed it so that all inertial frames are simultaneously treated as the single preferred frame, as a single preferred frame. And it turned out, when I looked into it a little differently, that was basically what the math law was prohibiting. You can't have the multiple base reference frames at the same time, because that leads to different, contradictions. So I would just say to keep that in mind about looking at things through a math lens versus a physics lens, because I think it harks back to what Ian was saying, that a lot of complaints about modern physics is that people are looking at it through abstract math lens without any physics model constraints, and there's a lot of criticism of relativity about that. One other question for the gravitational field equations. I've always thought of them as non-relativistic because you have a specific physical entity, and it changes space-time around it. And that's a single view based upon the reality of a massive physical Earth. So I think in terms of the original field equations, it's not relativistic. I don't know if you've ever thought about it in those terms. Like in special relativity, you can have a million different observers having a million different and contradictory views, and according to Einstein, they're all equally valid.
Right. I guess here's my thought experiment with how I view special relativity, is that if, let's just say you had, to me, it's when I say it's based on geometry, I mean based on how. So I view time dilation as a change in like the half-life of atoms, the vibrational energy that you would think in the wave and everything. So imagine you had a spaceship and you were traveling through space, and I had 6 clocks, and three of them were built one way, identical. Another 3 were built a totally different way. But you're in a certain speed in space, and they're all clicking at the same rate. If you increase your speed, let's say you increase your speed quite a bit, according to special relativity, you would never know that you were traveling faster in space. And the clocks all 6 of them would be ticking at the same rate. My view of it is that 3 of the clocks would be ticking at the same rate, and the other 3 clocks will be ticking at the same rate, but they won't be ticking together anymore. Right. So to me, that's the distinguishment that you can't. And which ones are right? Which ones clock tick at the correct rate? To me, it's based on the geometry of the clock in the medium itself as it moves. That to me is a simple kind of a thought experiment for the way I view it.
Okay, I sent you a paper on time, and I believe it will change your view. Although what you just described seemed to be echoing what I'm saying. I don't believe time is a fourth dimension. There's
I don't either.
No such thing as space-time. What time is a human construct that's emergent from looking at process rates within 3D.
Right. The way I view it is that we measure time and length through periodical phenomena, whether that is wavelengths, which is physical, spatial periodicity, or whether clocks ticking or something, or planets moving around. We measure time through periodical elements. And that is what I think time dilation is that it changes the rate of those periodical elements. They're not constant throughout the universe or in a gravitational field. So to me, that's what we view our own processes, even as we move, even as we think and everything, is based on vibrational phenomena that happens in our body based on our local ether density and strain. So to me, time is based, and space is based on these periodical elements, and that's what we're seeing change is the periodicity of these, and we interpret this as time dilation and length contractions.
Right,
and it's really special relativity that has got rid of this concept, because before that, I mean, even things like length contraction, Fitzgerald length contraction, they were talking about the forces on atoms, which, as they were moving through space, that would actually compress them. But special relativity is purely geometric, as you say.
Right.
And that's,
I don't like the term time dilation. That's why I misunderstood what your view of time was, because you were using that. Whereas I just think of it as changing process rates.
Changing process, right? That's imprecise, wording and stuff. I say time dilation, but to you it means something else. But we're still talking about the same thing. Vibrational rates of certain things happen differently in gravitational potentials and what we can think of as potentials and stuff. So I think that, to me, the problem is that we're describing those changes in process rate using changes of magnitudes of infinitesimals. To me, it's a language to describe a physical phenomena. That's what
Yeah.
infinitesimals are. Is I'm using these change of these magnitudes to describe this change in these process rates. That's to me is what it's all about. And so that's the whole problem about changing the volumes, changing the length, the coordinate systems. We're changing the spacing between points, or are we changing the process rate that is actually happening? And it's important how you describe it mathematically.
I've talked about retardation of process rates. That's what I've talked about.
Yeah.
Right,
Exactly.
but one thing we don't ever see is a stop in process rates. So if we have this vibrational medium, we can slow it down and we can speed it up. But like this, to me, this Brownian motion and stuff is, I have other research which I don't have published yet, which kind of goes into why we have this Brownian motion and everything, why the ether acts like it does. And to me, that's all it is if you were to look at the Brownian motion in another part of your in a gravitational field, you would see that things vibrate at different rates, even us. So that's why when we say time passes differently in a field, it's because your vibrational rates are actually different in that portion of the field.
Right.
Okay. Right. Well, anything else, Nick, before we move on? You could always come back if there's time.
Well,
thank you very much. Yeah.
I would
Go
just
ahead.
ask Jeff in his Nobel Prize acceptance speech to mention me. Okay.
Well, that's good of you.
No problem, Nick. I'll probably, you know who Fritz Zwicky is?
Yes.
Yeah, so yeah, he was considered a loon in his time and everything, and then later on they're like, oh, he was right after all. That'll be my luck in 500 years. So.
And then skeptics or dissidents, like many of us here, including myself, might say, well, very eminent people have won Nobel Prizes, but the converse isn't true. Everybody who's won a Nobel Prize shouldn't really be considered eminent.
Right. I very much agree.
Okay, well, thank you very much, Nick. I'll bring it down for the present now. Okay, well, by the way, just one more thing before we go to Michael has come back. And I don't know if there are references in your papers, Jeff. He says, can you work up a reading list for books you've found significant in your studies of this? Do you have some of these references in the papers you've
yeah, and that last Vixra one, let me see if I can pull it up here. I can give a list of books.
Yeah, it would be helpful even if we just rehearsed it very briefly.
I mean, there's a massive book called Gravitation by Misner, Thorne, and Wheeler, and because inside of this is when if you start looking at it and you think, well, when they start talking about perfect fluids and everything, they talk about energy density and momentum and stuff. And if you start trying to invert it, because it speaks very confidently about it, but if you start trying to say, how do I know that we're not looking at an ether theory here, then I think that helps. Let me see if I can pull up the other ones. Of course, there's that 17th century indivisibles revisited was very influential on me. And then of course there's the books by Amir Alexander. Let me see here at the end what I've got. The report of the Dark Energy Task Force, that is a paper by scientists for NASA and the DOE. That is very influential. And then, of course, Amir Alexander, Infinitesimal, How a Dangerous Mathematical Theory Shaped the Modern World. Here, I don't think I can do a screenshot, can I?
Well, you've certainly got the audience quite interested in this, and they want to follow it up. So I'm encouraged by that, because I thought a lot of people would be put off by some of the complexity of what you're talking about. But no, it hasn't really put people off. They want to learn more.
Okay, yeah. I mean, I would pull up the paper and just take a look at the citations in it and everything, and it will show you where I developed these ideas from, especially the fundamental flaw in that 17th century indivisibles, because what was surprising to me was that a lot of these paradoxes and stuff. I mean, they go in there and they talk about Kepler, and they talk about how he developed the sweeping of the space to describe orbits of the planets and everything, where we went from epicycles. And that's one thing I like to compare this to, is that, you can be, there was these thing called epicycles and deference. You ever heard of those?
Of course, yes.
Okay, yes.
Like
So
the Ptolemaic system and so on.
exactly, and you had all these little loop-de-loops that they were doing to describe retrograde of the planets and stuff.
Yeah.
And you could become it didn't matter how good you were at modeling these little loop-de-loops that the planets were making. You could be an expert at it, but you would, and supposedly you could keep making them more and more complicated to describe the motion of the planets. But you have to think it at one point though, is that helping anything? It wasn't until you had a simplifying assumption that, the elliptical orbits, until it said, oh, this simplified everything. To me, that's kind of the way I view SIPNI, is that, if we instead viewed everything through the lens of infinitesimals and their number and their magnitudes, that would simplify a lot of mathematics that we use to describe the universe. So that to me is that mathematics right now is in a blind alley using kind of epicycles and deference, and has no way out of it because it's not in their toolbox anymore. It used to be, but it's no longer in their toolbox to examine. So to me, that's kind of like how I view this research, is that we're in a blind alley still of epicycles and deference based on relativity, which is based on our understanding of Euclidean, non-Euclidean geometry.
Curve fitting. Is this one of the publications that you refer to? Jeff and possibly others may enjoy checking out a book by Robert K. Mass, Space-Time Dynamics of an Isotropic Nonlinear Elastic Continuum.
I am not familiar with that one, and I will definitely make a screenshot and put that on my reading list.
Cornelis has put that. Okay. Right. Well, now, are there any other people who'd like to come in on the green room? I see James Keane has actually made a number of comments in the private chat, and maybe if Jim will forgive me, I'll actually bring him up before he's put his hand up to address those points, because we haven't explicitly dealt with them. You're making a number of points with regard to your own ideas of binary mechanics, and you think there may be some conflict. I think, if I'm not going too far, or maybe there's some omission in the part of Jeff's ideas. Is that correct, Jim? Or have you any other general comments you'd like to make?
I think Jeff is doing some good things and some productive investigations. It looks like he's to me. It looks like he's on the road to binary mechanics and full quantization. He's only talked about the dx in terms of length. Binary mechanics goes with full quantization of energy, space, and time, space being for length. And so it looks like he's got 1/3 of the picture that he's on the road to. And I welcome Jeff to join in. Now, in binary mechanics, the dx, which is the primary length constant, is based upon empirical data, not on a bunch of math. So, or philosophies about what math might mean, what and so forth, because we don't have infinitesimals. With full quantization, length is quantized, period. We start with that assumption. And we've been able to derive the speed of light, Planck's constant, and electric charge, and some other parameters, electron magnetic moment, and so forth. So it's binary mechanics is more physics data oriented, and rather than, but it looks like the whole line of thought that Jeff has is he's on the road to binary mechanics. So, welcome, Jeff.
Well, okay. So here, from just what you said there, is that you're taking a fundamental constant of nature that you've measured, and you're using that as your basic of length, right?
Well, I wrote a paper deriving what I call the primary constants for length, energy, and time in kilograms for energy, which is, of course, convertible to joules or electron volts, length in meters, and time in seconds. And those are what I call the primary constants. So my dx, your infinitesimal element I've derived from observational data, which are the so-called fundamental constants, which I call secondary constants, because they're all based upon the primary constants for energy, length, and time that I discovered. And so it looks like you're on the road to the dx, which is about 2/3 of a femtometer is your dx, okay? And by the way, that does not change, okay? That's why it's a primary constant.
So that doesn't change no matter where you're at in the universe. That would not change relative to each other.
Well, there's nothing in the model that says it changed.
Okay.
So are you talking about Planck lengths, Jim?
Well, the Planck scale is basically derived from dimensional analysis of the secondary constants. The secondary constants being speed of light, electric charge, Planck's constant, and so forth. These are the secondary constants. They're all based upon the primary constants, which is the Keene scale for energy, length, and time. And in binary mechanics, we have to follow logic. In other words, we can't just dream up and say anything. And so there's no logical data that I'm aware of that indicates in any manner, shape, or form that these primary constants actually change. Your dx, Jeff, in binary mechanics is the same everywhere and does not change.
Okay. So I guess the difference between when I view, you're right, I review geometry as a language. It has, let's just say it has nothing to do with the universe we live in. And this is the way that we're manipulating this geometry. The question is can I take this manipulation the way I do this, and if I model it with this elastic medium, and I look at these together, does it model how our actual universe works? Does it model your Planck length and stuff like that? So I'm also looking at, why does general relativity work at all? And the reason I'm doing this is to say, are we mistaking these?
Jeff, excuse me, general relativity does not work. It's been discredited. I myself have written 2 papers, both of which discredit or exclude general relativity. So you're starting from a completely
right, but you still have to admit you still have to admit there's people that do believe in it for some reason.
Well,
are there not?
Well, certainly,
are there not? There are people that believe in it for some reason.
Why would they believe in it when it's been discredited?
Right. So why would they?
Well, that's not my business. People are free to believe. Sorry, I guess I have a liberal bent. I think people should be able to believe what they want to believe. That's not something that concerns me at all.
Right, but so I guess the question is when people find something compelling, why is it there a group of this group of scientists that find general relativity so compelling? What is the logical reasoning behind that? I mean, are they all insane, or is there a logical?
I guess you'd have to ask them.
To me, it's like I believe that they look at certain things, measurement of things a certain way, and they think of it, but there's another way to look at it. And so I'm looking at how is it they could believe this?
Well, for general relativity, they have no measurements which uniquely determine that general relativity is correct. They don't even know why the speed of light is the measured value that it has.
I don't disagree with you.
Parameter to the general relativity equations that are published everywhere. C is a parameter. Now, by binary mechanics, we've actually derived the value of C from first principles, which start with full quantization. And so, this is an achievement which, is unique in the world of physics.
Okay, so I guess the difference between you and me is that I'm putting even physics aside, even general specialty, and I'm looking purely at the concept of geometry. Leave physics out of it, and that's what I'm going to work with. Is what I'm going to work with is mathematicians to say what you're saying is not logically correct. Forget about physics model and everything, but what your basic underlying meaning and stuff geometrically is not correct here. So I don't even have to apply it to physics yet. I'm just looking at false proofs false mathematical proofs to say what you originally started with is false. So if I can, what's nice about that is I don't need
when
any.
you say you're not referring to me, right?
No, right. I'm not referring to you. What I'm saying is that when I do this,
you're free to put physics aside, and I'm just here enjoying the show, my approach is more physics oriented. I use actual measured data,
right.
and there are many labs around the world which are confirming all of the predictions that binary mechanics make, and this is all experimental data. The most recently being the fractional electric charge for the electron, which look up John Low, Junglo at MIT in a paper in Nature. So this confirms fractional charge, the binary mechanic model of the electron. But if you want to deal with the math only, that's fine with me. That's,
anyway, the bottom line is your initial comments, if I may try to interpret them, were that you thought you saw a conflict in maybe your different ways of looking at this. But I think you've having heard the talk and now the discussion, you're now coming to the decision that, or the conclusion, Jim, that there are complementary ways of looking at things. There's not that much difference between Jeff's ideas and yours. See, Jeff is talking about,
yes. That's why I was saying it sounds like it's the road to binary mechanics. On one slide, though, it seems like he supports special relativity, at least on the two bottom bullet points on the equations where he's talking about time dilation and length contraction. I'm not sure whether, I don't want to put words in Jeff's mouth. Do you support that there is length contraction, that these little dx's change?
I do support that. I think that.
Okay, what is your evidence for that?
So let's put it this way. My evidence would be like I said, the model. If you could actually do the experiment, but I can't actually do the experiment to say that you can actually have clocks ticking differently in one frame of reference versus another. That would be my evidence that the dx's between the two different clocks aren't the same, and the dt's aren't the same.
Well, gee, that sounds beautiful, but that's a long, multi-word statement that you have no evidence. So
you're right. I don't have an experiment right now.
I might suggest to you that you look for a more evidence-based approach, because in the end, it's the real world is the test of our ideas.
Yeah, he doesn't, and we don't have evidence of length contraction. But this time variation in atomic clocks. Now, the mainstream, most people, and maybe Jeff, you agree with this, I don't know, would interpret that as confirming time dilation, whereas I think Nick agreed and so on, say, and I thought what you said earlier, Jeff, may have concurred with this, that these are just variations, physical variations in physical processes.
I agree with that.
Vibration, the frequency of cesium atom vibration.
Yeah.
And so on.
I think we're saying the same thing, but I guess
the energy density of the clocks up in space in satellites is much different than the energy density at the surface of the
gravitational effect. Yes.
And so that there's all sorts of explanations for that. You see, for these theories, which you seem to be ready to embrace, they require evidence which is unique to that theory. For example, gravitational lensing. Well, we already knew that there's lensing. The eye has a lens in it. If you have a telescope, you understand that there is lensing. And so, in fact, if light is lensed when it passes by a star because of the increased energy density around it, you've got a lens. There's nothing that has anything whatsoever to do with necessarily with gravitation per se. And so, general relativity, as far as I know, there's not a single piece of evidence which is uniquely indicative that only general relativity explains or accounts for that evidence and not some other approach. Please,
I think
hope
we're
there's some.
Okay. Could you answer that briefly, Jeff? Because I know there are one
Yeah.
or 2 points that you yourself
Please.
want to come back on. And if we could leave it then, Jim. So just
Yes.
please, very briefly, there are 2 points you want to raise.
well, I just want to be
Thank you.
careful here that when I say time dilation, I guess it's the problem with the wording and stuff is that I am talking about the physical processes being different, that they're doing at different rates. So I guess whenever I think what is people have been seeing the natural philosophy side a long time, consider when you say time dilation, it means something else. So I don't want to represent what my meaning. I am talking about the physical processes being different, but we describe.
Okay, well, that agrees with Ian, Nick Percival, and James Keane.
Yes, I am talking specifically.
And by the way, thank you Jeff for presenting today. You're a very smart guy, and I really enjoyed your presentation, sir. Thank you.
And thank you very much, Jim, for your contribution. And we'll no doubt be talking about this further, maybe among ourselves.
James Arathun, he said something about
exactly. So
he said, the axiom of choice normally refers to an axiom of set theory.
Yeah, I want to
what is the connection? And very, very, very true. And actually, that's where I came up with the name, was the kind of the same process of the axiom of choice and set theory. And that
I brought James up there. So
so you have this unconscious choice of you making that you don't realize that you're actually doing it and everything. It's the same thing with the axiom of choice in NM. That you don't realize that you actually are choosing to change lengths and everything based on the number or based on the magnitude. So it is. I did kind of model the name of this axiom of choice off of the axiom of choice in set theory.
Okay, so you were bang on. It is. There is a strong connection with set theory. Well, in fact, Jeff was spurred on to that by the thing. So your observation was bang on. We're running out of time. If you want to make a very
make a quick comment,
James. Yeah, go ahead.
So we're not all seen as having the same views, because I don't necessarily have the same. In my I think it was my second talk, I talked about the necessity in physics that you have a system of units. So in order to measure real things, you can't actually measure a height of a tree. You have to have a stick and then have a standard. So all our measurements are ratios. So within the frame, if you have a slight change due to the speed, it's ratioed out. So you can only compare or see, I think, clock changes between when you compare rates between two frames. You can't, even if within the frame you change speed, the clock will change. You can't observe it. So that's the first point. The second point, which is more linked with what you're trying to say, is about general relativity, is that when I've had views from Denny and one or two other people, they say that almost they want to produce general relativity in terms of electrodynamics. So they want to have a varying C. So in space, so when light is deflected by a sun, say, or some other huge mass, it's due to the fact that there's some sort of refraction happening in space. Now, the whole point of general relativity is it fixed C and used the mechanics of varying infinitesimals as the way of almost having a standards lab at every point in space. So the previous idea was have one standards lab, and we define everything on Earth and make reference to that. In general relativity and even special relativity, that's been swapped. So every point in space has its own standards lab. Can you make a comment?
No, I think I do agree with you about relativity, that you don't have an absolute unit of time or an absolute unit of length. I can only compare a length of one thing. If it changes, I can only compare it to what it was or a different length. It's all relative to each other. There's no absolute. So, and in general relativity, right, they consider the speed of light, like you're saying, at every point to be constant, this constant C. To me, it's like, well, how would you know the difference between that and a change in physical rate of the vibrations and the change in wavelength? What if those are approximately a constant ratio? That would look very much like the constant speed of light. at the saying that this photon can move through space and everything. But if the photon changes wavelength and the time rate right there, the physical process rate changes right there, they're mistaking that for the speed of light, when actually you're looking at a ratio of wavelength change versus process rate change. And I don't buy for that it's actually even constant throughout the space and everything. I think that's one thing we're going to find out is that light speed itself is not. I think it's very similar in places around stuff, but I think that we will find out that there is a small difference in it. But I do agree with what you're saying there.
Two other comments we don't really need to know.
If you could be very brief, James, because we're running out of time.
A guy called Myron Evans who created general relativity, but with extra twist in space. Now the actual academic relatives went after that and have totally crushed it. So any changes to their thesis, like putting a twist, and that causes even more problems. But why not have a twist? I mean, if you've got no understanding of what space is, if it's not relative to anyway, that's a comment. And the other comment was retarded potentials. So general relativity by default doesn't have retarded potentials built in, or retarded action at distance, which is the other way of talking about it. And when you put in that, according to some researchers, it changes the whole theory. The predictions. So
retarded by the speed of light.
Yes, there has to be retarded by the speed of light. It takes from the sun 8 minutes for light. So any change from this in the sun, instantaneous change, has to take 8 minutes and you have to allow for that if you're doing the physics properly.
I guess I'm not. I have to look into that more. I don't think I understand the reference to what it means by retarded by the speed of light.
Yeah. You just put in a time delay, so there's phase differences entering your theory.
Yeah, and I mean the theory of relativity, I suppose, would say that delay would occur in gravity because gravity travels at the speed of light, the gravitational interaction. Whereas many of us would consider that that's not the case. It travels very much faster. There's effectively almost instantaneous reaction. But anyway, James, if we could leave it there, thank you very much. We'll have to come back to many of these issues.
That was a great talk, by the way. Yeah, cheers.
Oh, thank you, James.
Thank you very much. Thank you very much. So just before we end, I want to do two things. Just for maybe a second or two, I'm just trying to bring James down there. I think we've run out of time. I think Vladimir, but let me just see now. Sorry, just panicking a bit now. There's James. Yeah. No, it's just Nick has mentioned one thing. We don't have to bring him up again. We don't have time, unfortunately. But he says he's questioning the value of the small time that you talked about, Jeff. He says, I think your fundamental length is way too large. Please repeat that length magnitude. I don't know if you have an answer.
Mine, or was he talking about?
I think you remember when we asked you, you gave an order of magnitude of the, or maybe he did.
That was, I believe, was James Keen.
Oh, it was James Keen. Yeah. Okay. Yeah. Okay.
Because I'm not. I understand that we have like the Planck's constant and all these other stuff. So this specifically, what I'm not talking about here, I haven't yet gone into that type of thing where the wave theory itself. This is more of a broader overview because I think once you get in, because I do believe with this, you could actually recreate the quantum mechanics and you could have a unification between what general relativity should be and what quantum mechanics should be. You can write them in this different language and you'll be able to unify them. So, but that's a couple of years down the road.
Okay, so, there's some more work to be done on that.
Yeah.
Could I just very, very briefly, because you were dealing with very fundamental concepts in pure mathematics, and Denny, if you don't mind me just putting you up for a very, very brief period of time, if you could give a reaction as a mathematician to Jeff's whole concept of, casting doubt on this whole differential business, I suppose the differential calculus, the basis of it, and how he's applied it. Have you any view at all? Do you think there's any merit in it, or do you take exception to it, or do you agree in certain aspects and disagree in others? We'd value your comment, Danny, as a mathematician.
Yes. There's a number of different mathematics that have been thought up to describe reality. Professor Santilli of hadronic mechanics, who has this hadronic journal, has his own integers called the isointegers. And he developed this because he followed Paul Dirac's approach to a negative mass, matter, and negative energy, and so on. And he found that that allowed him to, for example, he has an operational hot fusion device. It's operational, it's been tested, but he can get no one interested in it because the math is completely different, starting with the integers. And then there's this fellow down south who I can't, whose name completely escapes me, who was in magnetics, and then he went into sports physics. And he noticed that everyone was always having trouble with getting the sign right in all of their calculations, the algebraic sign. So he developed math without any negative numbers to describe physics. And this guy's not a crackpot. Now he's into sports physics, namely golfing. He's making a fortune. He's training people, and then they do better on the tour as far as winning's concerned. So he's not a crackpot. Although it sounds like without negative numbers, but there was a time in mathematics when there were no negative numbers. They were developed later on. For example, the people developed the cubic equation solution and the quartic equation solution. They used negative numbers. They weren't around.
The Greeks really didn't have negative numbers.
What?
The Greeks didn't have negative numbers. Isn't that true?
No,
it was really
but I mean,
later.
More recent than that.
Yeah.
They followed the Greeks for a long, long time. And right. I think that your theory has a lot of merit too. But the problem is the same that Professor Santilli is facing. Namely, even though he has an operational hot fusion reactor, the fact his math is so alien to what the usual variety is, he can't get anybody to go with it. Because the engineers wouldn't be able to understand how the thing worked and build different, larger and smaller and what have you, versions of this reactor. And so he's stymied.
Right.
I wrote my newspaper, the Epoch Times, a letter to the editor trying to get them to publish it, but they wouldn't. Here again, it's just a matter of no one wants to have to learn a new math.
Okay. Have you any brief response to that, Jeff?
I would be up against the same type of thing. The only difference is what I hope is that there are some of these problems I've shown in here, which maybe to people in natural philosophy aren't really important. They are important to certain mathematicians, historians, and stuff. So if you've written a whole book and described, hey, this is one problem nobody's ever figured out, it's just an interesting thing. I think as long as I can start to talk to certain teachers and say, I can solve this problem, which was not solvable before. I can solve it with this new notation, which is the same problem like the person Dennis is talking about, is why would you bother learning this new notation? And when I say, well, with this new notation, you can actually describe this problem in a different way. And it's simple. It's not. And so it gives them a thought experiment to try to resolve something, but isn't involved with physics. If I can do it piece by piece by piece by piece, then maybe I'll have a chance that the gentleman.
I think selling it to mathematicians would be a lot easier than selling it to physicists.
I think you're right.
I think you're definitely quite correct.
Okay. Well, thank you very much. Thank you, Danny, for those comments. But by the way, I think I've solved the problem. Nick's point. I think he misheard. James had talked about 0.67 femtometers, and I think he misheard it as centimeters instead of femtometers.
Quite a big difference here.
Yeah, indeed, quite, yes. So it's fine. I'm sorry, the time has caught up with us on with a vengeance, but I mean that's positive as well. It indicates that despite the abstruseness of your subject, you have enthralled us all, and you've kept our imaginations going and the questions flying. And I'm sure there will be repercussions in the coming weeks from what you're talking about. We have, for example, cosmology sessions on Sundays with Harry Ricker, and I'm sure he'll refer to your talk today. So what I'm going to do now is give you the floor for a minute or two maximum, if I may, Jeff, just to summarize. If there's anything that has arisen as a result of the conversation or questions, you could just pop it in now, and then I'll come back and formally close the meeting. So I'll give you a minute or so again on it.
Okay, so what I basically hoped here was to bring up some questions in people's mind. Some people believe in general relativity and special relativity, but what I want to reframe the question is what do we mean when we say we measure stuff? Is it all of our measurements relative? And this is what our models actually are, is they're actually a language to describe measurements. And they can be measurements of anything. You could take a number of people passing through a gate, and I can integrate that to find out how many people are in there. But we also use these equations and stuff to model how our universe works. It is not the universe itself. It is just a language for describing it. What I hope to bring up was that people's thoughts about measurement is that, are we using coordinate systems to measure things, or should we be using these other things, which were elements of length, volume, area, and volume and stuff? And that's my question I want to bring, is that all I'm doing is saying we're using the wrong theory of measurement, coordinate systems and everything. We should be using these other thing called infinitesimals. And we combine that with models of an elastic material, a very stiff elastic material. And should that describe our universe better? And to me, if you step back and you think, well, where did this start from? And it started from in the 1600s when we couldn't understand what an infinitesimal was. So I think if we resolve that, I think that we can make a progress in our understanding of how our universe works. And we can get away from some of these concepts, which are actually just, to me, they're science fiction, multi-universes and stuff like that. We go back to a more sensical model. And to me, general relativity, I don't have a choice. General relativity started out with these fluid equations in there, which are like elastic material. And if you invert it, you get an ether theory. To me, it's kind of a more of a common sense approach. So hopefully you found this presentation entertaining or somewhat informative. Thank you very much.
Well, there's a simple answer to that. We certainly did. That was evidenced by the number of questions and the number of very interesting points, which could have given rise to a lot more discussion. And unfortunately, we've just had to curtail it. We've overrun by a few minutes as it is. But when I was discussing some months ago, actually, with Jeff, the possibility of expanding on his earlier presentation to us, I didn't really think that it would result in such an amount of interest that it actually has. Sometimes people are put off by mathematics. Some of the earlier comments actually were, "Oh, I'm not really au fait with mathematics, and it puts me off," and that sort of thing. But no, people have listened to your very fundamental points, and I think it's very useful to have those described, through video sessions such as these, because some people who are not terribly conversant with mathematics might have been put off by looking at the paper which Jeff has produced at the start. But now that they've actually heard him, I think it will be easier to go back to the paper and maybe fill in some of the gaps and have a look at some of the references. So therefore, with sincere apologies for having rushed the end of this, I'd like to thank all the participants through Facebook and YouTube for your very fine questions and your discussions and for your attention. I'd like to thank everybody in the green room. Everybody, I'm sorry I didn't get to every single person, but we'll do that at some later stage. And those of you who did contribute, I had to cut you off a bit. I'm sorry about that. But thank you very much for your contributions, all very, very positive. And of course, last but not least, our speaker today, Jeff has gone to a great deal of trouble to produce a presentation which would describe the essentials of his very considerable research over a long period of time, and aided with this, very, very substantial visual age, which I think have helped us considerably in thinking fundamentally about not only physics, but about the mathematics that we've been brought up with. Mathematics maybe dating back hundreds of years, and Torricelli, who's the pupil of Galileo, and so on. So thank you very much, Jeff, for having spent the time with us today and being very patient in dealing with all the questions and answers. So without further ado, I really have to close the meeting now. We're 10 minutes overdue. Thank you all very, very much indeed. And thank you, our speaker, for his presentation. I look forward to coming back and giving a talk the next time. So good day to you all, wherever you are.